In this lecture, we are going to have a quick introduction and some basic fundamental ideas and historical developments in the context of communication systems. And then we'll also see what are the different types of channels or the broad categories of channels that we are going to consider in this course, and also the mathematical models for those channels. Okay, and we'll begin with the basic elements of a communication system. So in a typical communication system, we have an information source which produces the information that we want to communicate. So that would be represented by a block which we can call as information source. And from that information source, the information that we need to transmit would be sent to a transmitter. So that goes to another block which we call as the transmitter. And the signal that is transmitted will propagate through the communication channel. So the next part of the communication system is the communication channel. So our next block is the medium of propagation through which the signal that we transmit from the transmitter will pass through to reach the destination, which is called as the receiver. And then the signal that the receiver receives has to be decoded or converted back into a form that is useful for us. For example, if the information source was coming from a source of sound, for example, then that source of sound would be converted into an electrical signal by the use of some transducer, like a microphone, for example. And then that signal would be processed by the transmitter, and the processed signal would then be transmitted over the channel, and the receiver gets that processed signal, and the receiver has to recover the original information signal and then pass it on to the output transducer, which will convert it back to the original form. For example, if it was sound, it has to convert it back to a sound. So the sound is converted to an electrical signal by a microphone here, and the electrical signal has to be converted back to sound through the output transducer, which would happen in the form of by means of a speaker, for example. So the last part would be the output transducer. And corresponding to the output transducer at the information source, we will also have the input transducer. Okay, for example, if it is voice or sound signals, then the input transducer is a microphone and the output transducer would be a speaker. If it is some other form of signal, the transducers would vary. So basically, the information or the information that we want to transmit has to be converted to an electrical signal by the use of a transducer, and the transmitter will perform certain operations on that particular signal and put it on the channel. So therefore, the job of the transmitter is to represent the signal in a form that is suitable for transmission over the communication channel. And one of the important things that the transmitter does is what is called as modulation. So that is something that you have come across in your communication system course. So the functions of the transmitter. So let's list down what are the functions of each of these. So the transmitter, among many things, one of the important things it does is called modulation, whereby the signal or the information that we want to transmit is put onto a carrier signal by modulating or varying one of the parameters of the carrier signal. Like if you vary the amplitude of the carrier signal, we get amplitude modulation. If you vary the frequency of the carrier signal, we get frequency modulation. And if you vary the phase of the carrier signal, then we get what is called as the phase modulation. So in modulation, we can have three types, which is amplitude modulation, AM, frequency modulation, which is FM, and phase modulation, which is PM. Now, what kind of modulation is used at the transmitter? That depends on several factors, such as the characteristics of the channel and the bandwidth available on the channel, and the propagation properties, and also the kind of hardware or electronics devices that are available for the purposes of the transmitter, for implementing the transmitter. So based on a variety of factors, the choice of the modulation scheme can be chosen accordingly. Okay, and some of those important factors are the bandwidth of the channel, the characteristics of the channel itself, and also the available electronic hardware. And other operations or other functions that are performed at the transmitter are filtering. So okay, we want to, for example, have the signal that we want to transmit as uncorrupted as possible. So if there is any corruption on the signal, we want to minimize that corruption before we even send the signal on the channel, because the channel is going to add more noise and distort the signal even further. So we want to make sure that the signal that we transmit is clean to start with. So filtering is performed for those purposes. And we want to another operation that the transmitter could perform is amplification. Okay, that is to amplify the signal to have sufficient power so that it propagates over the channel in the presence of the noise and reaches the receiver in a form that the receiver is able to detect and recover the original information from the received signal. So amplification is also another important aspect that is performed by the transmitter. And a further function of the transmitter could be radiating the signal through an antenna. So that happens if the communication is over a wireless channel. So in that case, another function of the transmitter could be radiation over an antenna. Okay, so these are the broad functions. Okay, of course there are many more functions that are performed at the transmitter side in modern day communication systems, but talking of a basic communication system, these are the typical functions that are performed by the transmitter. We'll go into the more detailed aspects subsequently, but to start with, let's consider that these are the main functions that the transmitter would perform, which is modulation, filtering, amplification, and in the case of wireless transmission, it should also radiate the signal over an antenna. The next block that we have in the system, in the communication system, is the channel block. So we'll now discuss a few things about the channel, and later on towards the second half of this lecture we'll discuss the channel in more detail. But let us start with some basic description of the channel and what happens to the transmitted signal on the channel. So one of the things that happens on the channel is that the transmitted signal gets corrupted. Transmitted signal gets corrupted as it traverses through the channel. That means as the signal passes through the channel, it gets corrupted by a variety of sources and causes of corruption. So one of the most common types of distortion that happens on the channel is because of noise. So one source of corruption of the signal is noise, and the noise is typically random in nature. So we have to deal with the probabilistic models to characterize that noise, and also once the signal gets corrupted with the noise, then we need to use probabilistic tools to deal with the randomness and to analyze the randomness, and to also devise techniques or mechanisms whereby the effects of this noise can be minimized. Now, the noise typically is considered to be additive. That means the noise gets added to the signal that we transmit. So in that case, we call it as additive noise. Okay, and typically the source of such noise, where does this noise come from? It could be from external sources which are in the vicinity of the channel, or it can also come from the internal sources, which is from the electronic equipment comprising the transmitter and receiver itself. So one of the major source of noise is thermal noise. And thermal noise comes from the electronic circuitry itself. And the other sources of noise could include man-made noise, man-made noise that could be because of say some machinery operating in the vicinity, or it also comes from the ignition of automobiles, and also it can occur from natural sources like electrical lightning, right? During a thunderstorm, we can have electrical lightning that can cause that adds up as noise and affects the signal that is transmitted. So the next category is called as atmospheric noise. Okay, and typically the atmosphere, a particular source of atmospheric noise is the electrical lightning discharges from thunderstorms. And another form of distortion that happens on a communication channel is interference. Now, interference is the corruption of a signal by some other signal. For example, some other user would be trying to communicate and their signal would interfere with our signal. So basically, interference is the corruption of a signal of one user by the signal of other users. So the channel could be shared by multiple users, and the mixing up of the different user signals corrupting each other, and that is called as interference. For example, if we are sitting in a room and we are having a discussion, and if all the people start talking, then each one's voice becomes an interference for the other person's voice. So interference is comes from other users of the channel. Okay, so it comes from other users. So that's another aspect that we need to deal with when designing a communication system. And the third form of distortion that occurs is called as multipath distortion. And multipath distortion is basically the signal that is being transmitted reaching the receiver via multiple paths of propagation. And because each path would have a different length, the received signal would have would get multiple copies of the same signal, which are all shifted by a certain amount, resulting in the multiple copies of the signal being received, each having a different phase shift. And basically the receiver is going to add up those components, and if it because of the random phase shifts that are going to occur, the added up signal could either add up constructively if the phases are aligned, or it can add up destructively if the phases are not aligned. So that means there would be a random fluctuation in the received signal strength because of multipath propagation, and that process is called as fading. So as a result of multipath propagation, what happens to the received signal is called as fading, which is nothing but the random variation in the signal strength or signal amplitude that is received at the receiver side. And that happens because there are multiple components of the same signal reaching the receiver, each having a random phase shift. And because of the random phase shifts, if the phase shifts are like 180 degrees apart from each other, then they will cancel out each other, making the signal become zero. But if they are nearly 180, it will become very weak. But if they are in the same phase, when they add up, they will amplify. And if they are off phase, they're going to cancel out each other. So that causes random fluctuations in the amplitude, which is called as fading. So both these things, just as the noise component, which is random, the multipath distortion that occurs, that causes fading, that also has a random behavior. So we need to use statistical techniques of such as probability and random processes to deal and understand these processes, and we need to take into account these processes when we design our communication system. So multipath distortion and fading, it is also having a random characteristic. So we need to use statistical techniques to address these issues. And a more general phenomena that happens on a communication channel is called as attenuation. Okay, attenuation is nothing but the weakening of the signal as it propagates to the channel. So as the signal goes further and further from the transmitter, it becomes weaker and weaker. So we need to ensure that the signal is transmitted at a sufficient power level so that it reaches the receiver, or if the distance between the transmitter and receiver is too long, then we need to use intermediate amplifiers to amplify the signal so that it can reach the receiver having a desired signal strength. So attenuation is basically the loss of signal strength with distance. So when, for example, if I'm talking and if if the listener is standing 1 meter away from me, he might hear me very clearly. But if he moves 5 meters away from me, now my voice will become much more feeble. And if the person is 10 meters away, 20 meters away, and eventually at some point he won't even hear what I'm talking. So it's basically my voice signal is being transmitted at a certain power level. I'm speaking with a certain loudness, and with distance, this loudness is becoming weaker and weaker. The signal strength is becoming weaker and weaker as the signal propagates further and further through the channel, and eventually at some point it is so weak that the receiver will not even be able to detect the signal. So attenuation is also something we have to deal with. It is basically the loss of signal strength with distance. Okay, so that's another thing that happens on a communication channel. Let us now look at the third general component of the communication system, which is the receiver part. So the next component is the receiver, and just as we do modulation on the transmitter side, the important task of the receiver is to demodulate the signal. That is, at the transmitter side, the information signal is placed or is used to modulate the carrier signal by varying one of the parameters of the carrier signal, like amplitude, frequency, and phase. Now, the job of the receiver is to demodulate that signal, demodulate the modulated carrier, that is, by observing the variations in the amplitude, frequency, or phase of the modulated carrier that is received. So the receiver has to perform demodulation, and depending on what type of modulation is used at the transmitter, the corresponding demodulation has to be applied at the receiver side. So for AM, the receiver has to do the demodulation of AM, and for FM, the demodulation of FM, and for PM, the demodulation of the phase modulated signal. So one of the important tasks of the receiver is to perform demodulation. Now again, the performance of the receiver or the quality of the received or demodulated signal that is recovered after demodulation at the receiver, that would depend on what kind of modulation we have used, what kind of channel the signal has propagated through, and how much noise has got added to that particular signal, and what has been the what is the kind of amount of interference that has happened to that signal. So it basically depends on a lot. It depends on the aspects of the channel that have corrupted the signal before it reaches the receiver. And we need to design our system so that the communication system is able to deal with all these causes of distortions on the communication channel and be able to recover the signal with high fidelity. That means the received signal that is recovered should be as similar as possible to the signal that was transmitted, that is the information signal that was transmitted. So that depends on the factors of the channel that we have stated already. And apart from demodulation, the other functions that the receiver performs is filtering. Okay, because the channel adds some noise and the receiver must make sure that the noise component is removed from the signal component. So to separate the noise from signal, some form of filtering would be used for suppressing the noise. So filtering for noise suppression. Okay, so these would be the broad categories of functions of the receiver. Of course, if it's a wireless signal, then just as we used an antenna at the transmitter side, the receiver would also have a receiving antenna to receive the wireless signal that is coming towards it, right? So the receiver could also have a receiving antenna. If in the receiving antenna for the wireless case. Okay, so that's the very broad functionalities of the broad categories of the components in a communication system. Now these are very generally broad categories, but so far what we are discussing is we are just talking about the information signal modulating a carrier signal. So we're dealing with analog domain. We are considering that the information signal is a continuous function of time, the carrier is a continuous function of time, and the entire process is having an analog form. So the block diagram that I've shown now and the components that I've described so far, these correspond to a basic analog communication system. Okay, but this course deals more with the techniques that we're going to use for a digital communication system. And in a digital communication system, there are much more functions that are performed at the transmitter side and also at the receiver side. So the transmitter block itself could be separated out into multiple blocks, each performing its own function for its own purpose. So there are good reasons why we perform those functions. So now we'll look at what the block diagram looks like for a digital communication system, where we will highlight the main functions or implementations that we do in a digital communication system. So first of all, before we go into the digital communication system, let us quickly review what is a digital signal itself. So in the analog communication system, we are dealing with some waveforms, but in the digital domain, we are dealing with bits. So and so on. So the analog signal is converted to a digital signal or digital data, and that digital data could be represented as some form of pulses. So a 1, a 0, a 1, and so on, right? So depending on what is the value of the bit, we'll represent it with some form of a pulse, and that will give us a digital signal. So we perform analog to digital conversion, A to D conversion, to convert an analog signal to a digital signal. And in some cases, the source of the signal itself could be discrete in nature. Like, for example, if the source is coming from a digital machine like a computer, it is inherently digital or discrete in nature. So in that case, we need a digital communication system. So we convert the analog signal to a digital signal, and then use this digital signal for representing our source of information. And why do you want to do that is because digital communication provides several advantages. So let's ask why digital. One of the things that we can do with digital is in the analog signal, it could have a lot of redundancy. That means a lot of unwanted information that is going to occupy the channel bandwidth and resources. So by converting it to the digital domain, we can get rid of those unwanted components or redundancy. So in digital, we can perform what is called as compression. So we can compress the signal to remove redundancy. Okay, that is called as source coding. So we basically try to compress and represent the signal with as few bits as possible, while maintaining the quality of the original file or original information source. Okay, and that is possible in the digital domain. The other aspect of digital communication, what makes digital communication attractive, is that the effects of the communication channel can be dealt with in a better way in a digital communication system. So channel impairments can be handled better. So we have good techniques which will combat the effects of the channel, like the noise, interference, multipath propagation, right? All these can be handled in a better way so that the what we call as the signal fidelity can be improved. So that means the recovered signal would be much more closer to the original information signal in terms of its in terms of the values of the bits in this case. Okay, to improve signal, what we call as fidelity. Okay, so that means the received bits would be as close as possible to the transmitted bits. That improves the signal fidelity of the received signal. And the third advantage or reason why we would use digital communication is because another advantage is because if the distance between the transmitter and receiver is too large, then in an analog communication we use what we call as repeaters, which are amplifiers that keep amplifying the signal. But in a digital communication system, rather than simply using an amplifier, we can simply recover the original bits and then retransmit them forward to the next intermediate point or to the final destination, right? So that makes that prevents the amplification of noise, because each time the signal gets amplified at an intermediate point, the noise that has got added to the signal that also gets amplified. So that causes a more severe effect of noise on the signal. But in digital, we can simply recover the bits and retransmit them again forward, rather than simply amplifying the signal. So that makes the digital propagation or digital communication more attractive. And finally, there are a lot of good signal processing techniques which can be applied for the digital signal for a variety of purposes. We have seen compression already, and channel impairment dealing, that is called as channel coding, and We can also do encryption for security, for example, because a lot of sensitive information, personal information is being transmitted nowadays. So we want to make sure that it is protected and it's not stolen by unwanted people. So encryption becomes possible if we have our signal in the digital domain. So that's another aspect or a reason why digital communication becomes useful. So the third aspect why digital is attractive is because of security. So we can have security to our data so that the unwanted people or the unintended receivers don't get a hold of our data. So let us now have a quick look at the block diagram for a digital communication system. And like before, we have a source of information, an input transducer that produces the information signal. And here we would consider that the information signal is digital in nature, that is in the form of ones and zeros. If it's an analog signal, then between the information source and the source encoder, there is a component that would be called as an A to D converter, which is the analog to digital converter. And once we have the signal in the digital form, then one of the aspects that the transmitter side does is called as source encoding. That is basically to remove the redundancy present in the signal, and that's basically compression. For example, if you have an image file, you can use JPEG compression to compress the file and represent it as in JPEG format, which would make the file size much smaller compared to a .bitmap format, right, than the uncompressed version. So that means there's a lot of redundant information in that image which could be removed, and the file size can be made smaller without affecting the qualitative appearance of the signal. Okay, quantitatively, of course, there would be some difference. Again, that depends on the type of compression. Okay, there are two types of compression called as lossy compression and lossless compression. So in lossy compression, of course, there's going to be some degradation in quality, but as long as the end user is not able to perceive that degradation of quality to a significant effect, then we are okay with that, right? So source encoder is used for compressing the signal, and channel encoder adds additional redundancy to protect the transmitted bits from the effects of the channel. So the channel adds noise, interference, there's multi-part propagation and so on, and that would cause some of the bits to get corrupted. For example, we could transmit a 0 from the transmitter side, but the receiver detects it as a 1. That means a 0 has become a 1, so that's an error. And the channel encoder implements certain mechanisms on the bits by adding some additional bits, using which such errors can be detected and also corrected. And if the decoder is not able to correct those errors, then it will ask the transmitter to retransmit those bits. So the job of the channel encoder is to develop or to implement some functionality which allows the detection and correction of errors in the bits. Okay, and then we have the digital modulator, which is going to again use a carrier signal that would be modulated by the digital signal which comes out of the channel encoder. So the digital signal here would be a sequence of pulses representing the zeros and ones, and those pulses would eventually modulate a carrier signal, which is typically again a sinusoidal signal. So even in a digital communication system, the signal that propagates through the communication channel, through the physical channel, is still an analog signal. But we do all the processing in the digital domain, and that digital signal modulates the analog carrier, and we call that as a digital modulation because the information signal that modulates the carrier is a digital signal. So we have a digital modulator, and again, like in the analog modulation where we had AM, FM, and PM, there are several variants of digital modulation. Like the digital equivalent of AM is amplitude shift keying ASK. and for FM the digital equivalent is FSK, and for PM it is PSK. And furthermore, in digital modulation we can have what is called as higher order modulation schemes, whereby we can represent the more symbols, more bits in a single symbol, so that increases the bit rate. Okay, we'll come to those aspects later. So in digital modulation, just let me write down the basic types. That's amplitude shift keying, frequency shift keying, and phase shift keying. Then we can have higher order variations of these, which are called as let's say QPSK, 8PSK, and similarly we can have a QAM, and there's a higher order variant of QAM called as 16QAM, 64QAM, 32QAM, 128QAM, and so on. Again, we'll come to those topics later. Basically, the idea is that with the transmission of a single symbol, we want to send through as many bits as possible. So with QAM and 16QAM and 32QAM and so on, we are trying to send more bits within the same symbol, and we do various techniques to achieve that. Okay, so that's the job of the digital modulator. And finally, when it passes through the communication channel, the received signal is going to be corrupted by the various distortions that can occur in the channel. The first is the signal will get attenuated, which is the loss of signal strength as it propagates through the channel. It could be affected by additive noise, which is random, and there could be multipath propagation, because of which there could be fading, and there could also be interference from other users' signal, which has got mixed up with our signal. So the job of the receiver is now to negate all the effects of the channel, and as the first step it has to do the digital demodulation to get back the signal from the carrier signal, the modulated carrier. And then the channel decoder will do the reverse operation of the channel encoder, that means to detect and correct the errors. And then the source decoder would do the decompression part, and finally the decompressed bits would be given to the output transducer, which would generate the output signal in the form that is desired. Okay, so that's the broad aspect of a digital components of a digital communication system that we have shown here. Next, we are going to discuss some important findings in the early literature of digital communication, and those findings have become like the foundation of modern digital communication systems. Those were the first kind of breakthrough research findings for digital communication systems, and they kind of lay the fundamental limits to what we want to achieve, or what can be achieved over a digital communication system. And one important such finding is what is called as the Nyquist rate. Nyquist rate, and what does that mean? And obviously it goes by the Nyquist rate comes from the name of the scientist who investigated on this topic and came up with his findings. And what this Nyquist rate says is that if we are representing our bits in the form of some pulse, okay, so let's say we have a rectangular pulse, right? Rectangular pulse. Obviously, we never transmit rectangular pulses in practice, because rectangular pulses, if we take the Fourier transform of a rectangular pulse, it is a sinc function, which means it has infinite bandwidth. So normally, we use a pulse, we shape the pulse in such a way that its frequency domain representation is band limited. So if we say that the pulse shape, so let's say we consider a pulse shape band limited to some bandwidth W hertz. So if the pulse that we have designed is band limited to W hertz, what Nyquist went on to explore is that, or investigate, is that what should be the maximum pulse rate, or how many pulses we can transmit per second without causing intersymbol interference. That means without causing one pulse and a neighboring pulse interfering with each other. So the question is, what is the maximum pulse rate without causing inter-symbol interference, which we call as ISI. Okay, so that's the question he set out to answer, and from his research what he concluded was that the rate at which you can transmit the pulses, okay, suppose the width of the pulse is a certain t, then the rate becomes 1 by t. So pulse rate equals 1 by the duration of the pulse. Okay, so that's 1 by t. It's called the pulse rate. So if we transmit faster, if we transmit more pulses per second, that means the width of the pulse has to be smaller. And if the width of the pulse is more, then 1 by t becomes larger. That means we are transmitting at a slower rate. So he set out upon what is the maximum value that we can have for this 1 by t without suffering from intersymbol interference. That is, without two neighboring pulses interfering with one another at the receiver side. So the conclusion was that the maximum pulse rate, which is denoted as 1 by t, is 2 times the bandwidth of the pulse, 2W, which is where W is the bandwidth of the pulse. So the maximum pulse rate is 2W pulses per second, and that is this is the limit. If we exceed this limit, it will cause intersymbol interference. If we are within this limit of 2W pulses per second, then it is possible to have the communication without intersymbol interference. So that's without ISI. Okay, so that's a fundamental result, and we will talk about this Nyquist rate again later, but I want to give you a quick introduction right at the outset because it plays an important role in a communication, in a digital communication system. And by the way, the kind of, or the shape of the pulse that that achieves this limit is what is called as the sync pulse shape, which is given by the function, if you can call it as g of t, as sine 2 pi wt by 2 pi wt, right? And basically it looks something like this. The sync function, it has a main lobe and it has decaying side lobes. So these side lobes keep becoming smaller and smaller and smaller, but they don't become zero until they reach infinity. So they become zero at infinity. So with such a pulse shape, we can have neighboring pulses arranged in such a way that when one pulse is going through its zero, we can have another pulse which is at its peak. So we can have the neighboring pulse going like this. So that way, when this pulse is zero, the neighboring pulse is at its maximum. So when this pulse is maximum, the neighboring pulse is zero. So that way we can sample at the correct instant, so that each pulse is only one of the pulses is having its maximum value at that sampling instant, and all other pulses have a zero value at that instant. So that means there wouldn't be any intersymbol interference. Okay, and that's the finding which is called as the Nyquist rate, which is 2W pulses per second with the use of sync shaped pulses. The next important result in the aspect or in the domain of communication, digital communication systems, is what is called as the channel capacity theorem. So it is also called as the Shannon Hartley theorem. And basically what this theorem says is that it gives us a relationship as to given a certain bandwidth for the channel. Okay, so far we have talked about the bandwidth of the pulse. Now, given that we have a certain bandwidth for the channel and a certain noise power on that channel, how do we decide what is the maximum speed or rate at which we can transmit our digital data? And that is called as the capacity of the channel. So that gives a fundamental limit. Okay, it places a fundamental limit called the capacity of a channel. Now, the capacity of the channel, which is denoted as C, is Shannon, in his paper, he proved that it is given as B, or the bandwidth W, logarithm to the base 2, 1 plus the power of the signal, which we will denote as P, the signal power, by N naught times W, where N naught is the power spectral density of noise. So that is the noise power spectral density, and W is the channel bandwidth. So if we have a wider bandwidth for the channel, that means the noise power is going to increase because the noise power is given by N naught times W. If W increases, the noise power spectral density gets multiplied with a bigger number, so that means the denominator is going to increase. And if we don't increase the signal power, that means the signal to noise ratio is going to become small. So this whole term here on the right here, this whole term denotes the signal to noise ratio. P denotes the signal power, and N naught times W denotes the noise power. Okay, so what Shannon showed here is that the capacity of a channel, which is the maximum rate at which we can communicate over a channel, depends on the bandwidth of the channel and the signal to noise ratio of the channel, and the capacity is given by this relationship W, the bandwidth times logarithm to the base 2, 1 plus signal to noise ratio. So that's the maximum bits per second. So that's the unit for that is bits per second. Now, what this limit says is that if we transmit at a rate R below the capacity of the channel, then we can have some kind of channel coding scheme like we had here, the channel encoder and channel decoder, some form of error detection and correction mechanism, which will ensure that the received signal has arbitrarily small error probability. The number of bits in error in the received sequence would become arbitrarily very small, very close to zero. So that is possible only if the transmission rate R is less than C. So that means if R is less than C, reliable communication is possible using some channel coding scheme. Now, Shannon did not prove what kind of channel coding scheme, but that is left as an open research topic where researchers have come up with newer channel coding schemes to get closer and closer to C. So, reliable communication is possible using some channel coding technique. Now, if R is higher than the capacity of the channel, if R exceeds, if we transmit at a rate more than the capacity of the channel, reliable communication is not possible. Is not possible, irrespective of the channel coding or any other signal processing that we can perform at the transmitter and receiver. So reliable communication is not possible irrespective of the signal processing at the transmitter or receiver. Okay, the transmitter I have written as TRX and receiver as RX. Okay, so basically the capacity C is a fundamental limit above which we cannot transmit data or transmit the bits, because if we exceed that, no matter what we do, we are not going to have a small error probability in the received bits. Okay, this is a fundamental theorem in communications. Okay, so these are the two important fundamental results that we will study in more detail later as well. So the first is called as the Nyquist rate, and that relates the maximum pulse rate that we can transmit given the bandwidth of a pulse, and the Shannon-Hartley theorem gives a capacity that is the maximum rate at which we can transmit over a communication channel given the bandwidth of the channel and the signal to noise ratio on the channel. Now again, one might ask that, okay, if the noise increases, why can't we simply increase the signal power so that the signal to noise ratio is higher? Obviously that is not possible because there is a power limitation, because we cannot increase the signal power as much as we want, because there is not enough source of power, first of all. That there is a limitation, there's a constraint on that, and secondly, transmitting at too much power, that would mean interfering with other users in a more significant way. So that's basically, if I say that, it's like if I want to increase my volume, my sound, the way I'm speaking, there is a limit to what is the maximum volume at which I can speak. So that's a limit in my transmit power. And secondly, if I speak too loudly, my voice is going to go into the neighboring room and disturb the people in the neighboring room in their conversation where they're having a discussion, right? So that is going to cause interference to others. So there is a constraint on the maximum signal power that can be transmitted. So there is a trade-off here. So depending on the bandwidth of the channel and the amount of noise power and the constraint on the transmitted signal power, there is a fundamental limit we have on the capacity of the channel. So I'm going to stop here, and in the next lecture we will be discussing about some of the channel models, okay, the broad category of channel models, and then I will also talk about the mathematical representations or mathematical models to represent the channels.